Good afternoon, everyone. I'm Floriana Petrone, an assistant professor in the Department of Civil and Environmental Engineering at the University of Nevada, Reno. And in my talk today, I will briefly present a methodology we have recently developed to guide the selection of ground motions for infrastructure assessment using sets of region-specific earthquake simulations. I am presenting this work on behalf of a number of co-authors, mainly my just PhD students, some of them former students now, and postdocs at UNR. Now, before getting into some technical details of what we have been working on just lately, I want to just give you a glimpse of what really just motivated our research and in this specific field and the development of this methodology. So, well, as we all know, the relevance of ground motion simulations to earthquake engineering applications spans across the two main pillars of earthquake engineering. Seismic hazard and structural fragilities, with the strongest interest in all those scenarios that are not well represented in the just catalogs of empirical data. And we mainly refer to the near field of major active faults, where we know ground motion are highly variable and so are structural responses, as also demonstrated by a number of historical events, including some very recent just large magnitude earthquakes. Now, we also know that in the very near field, ground motions are shaped by the details of the rupture, including slip distribution, rupture speed, forward directivity, and the way this can couple with the local site conditions. So, in this regard, suites of region-specific earthquake simulations where we can tweak, we can perturb on purpose the rupture parameters provide invaluable data to the engineers and analysts really to assess the expected demand on a specific basis in terms of amplitude and variability, very important, and also to fully understand what are the underlying causes for specific observed ground motion intensities and amplitudes we observe, especially when these fall outside the ranges predicted by the empirical models. Now, we actually started quite some time ago, a few years ago, looking into multiple realizations of large magnitude events, mainly for validation purposes, but also to provide the key elements to correctly interpret ground motion amplitudes and variabilities, especially in the near field, when these really just go outside what is our expectations, or as we know, the expectations and what are the predictions of the empirical models. And today I'm going to focus on what I call here this preliminary set of 25 realizations, and you can think about this as the generation coming just right before the latest generation of ground motions that are currently available on the database with the beta users. These are 20 realizations of a magnitude 7 Hayward fault earthquake, and here is the representation of the rupture models, which use the model proposed by Graves and Pitarka in 2016. And we also see that some of these realizations here, in addition of having this stochastic distribution of the slip across the rupture plane, also incorporate some deterministic patches with high slips. So, we have looked at the motions coming from these 25 realizations in several ways. We also looked at the implications of using these ground motions on the response of long span bridges, highway bridges, as well as a variety of just 3D and 2D building structures. And across all these analyses, we have observed consistent trends here in the ground motion amplitudes, which were clearly correlated with characteristics of the rupture models. This was the case, for example, of forward directivity effects, which ground motion simulations can fully capture, as demonstrated by this set of stations here highlighted in light blue that are located on the opposite side of the point of initiation, the epicenter, in this case of the rupture, where we know that we have the constructive interference of the waves leading to larger amplitude motions. So we looked at these motions in terms of waveforms and impulsive character, but then we confirmed the fact that these amplitudes, higher amplitudes, were correlated to forward directivity effects after comparing the peak ground velocities with those predicted by the model proposed in 2004 by Bray and Rodriguez. We took a step forward here, and we also compared the response of a building, just as obtained from the set of records here, forward directivity records, and a subset of just real motions, real records that are categorized as forward directivity following the criteria outlined back in 1997 by Somerville. And so you can clearly see like a good correlation here, really speaking to the possibility of using these motions to really supplement the just current database of records of for extreme cases, extreme motions. We have heard this morning, for energy systems, we want to use 1 ground motion to assess the response, but we want to make sure in specific cases that ground motion for a critical infrastructure is the one that corresponds to an extreme yet realistic event. Well, if you're really just interested in scenarios in these characteristics of the rupture that lead to extreme yet realistic ground motions, we may want to look at locations at sites where we have the concurrent effect of 3 just elements. So one is forward directivity, then the presence of a high slip patch along the direction of the rupture, and then local geological conditions. So in our case for the San Francisco Bay region, this was the case of the Pleasant or Livermore Valley, where we observed larger amplitudes, longer durations of the motions as an effect of the repeated refraction and refraction within the boundary of the basin, leading to, again, motions higher than what we would expect by just a straight, just comparison with the ground motion models. Pretty interesting here, we also noted some sort of pollution of the characteristics of the 2 components of the ground motions we're familiar with, so the full normal and full parallel component. And you can clearly see if we look at these are the just velocity time history for this site B here located within the domain. You can clearly see the similar character of the 2 components of the motion. So once again, we are looking at the full parallel and full normal. Now, at the end of this large set, I'm just showing here just a subset of all these analyses we have performed across a number of just realizations. Really, we realize how unique the characteristics of the ground motions in the near field can be as a function of a minimal perturbation of the just rupture model. And so, with this in mind, so we took a step forward and we decided to assess, to understand how these characteristics, especially in the near field, can affect structural response estimate when we follow code-compliant approaches. And in our case, we follow the SC7 approaches where we scale to the RODI 100 of the spectral amplitudes. Now, here I'm showing the map, these 2 maps, just kind of summarizing what is the just median demand obtained for a 3-story reinforced concrete building. And if you look at specific sites, as for example, this site A here, just located right on the just tip of the fault, you can clearly see that the median responses that we obtain are substantially different. And upon just a closer look at the just ground motions that we used, again, simulated motions versus just real records selected following the just conventional criteria. So really the key reason behind this difference was due to the polarization of the motions, which was consistently captured in the set of simulated records, but was captured to the same extent and not to the same proportion in the population of real records. And so for this reason, we decided to look more closely at this issue of the just polarization of the motions, and we selected 4 stations. You see here, this represented here by the just the fault from A to D. Here on the right, you can see the spectral acceleration generated across those 25 realizations for these sites, and clearly showing what we would expect, a broadband, larger amplitudes for the full normal compared to the full parallel component, and which is also confirmed by a number of ground motions from real events. So at this point, really just we ask ourselves, can we just leverage this rich population now of simulated motions to inform the current approaches for the selection of the ground motions, thinking about 2 main just issues. First, instead of targeting the RODI 100, the RODI 50, can we target spectral amplitudes for the separate components, for normal and for parallel? Keeping in mind and knowing now that this can be very critical in our assessment if we don't acknowledge the polarization to the just correct degree. And second, can we also target the variability for each component instead of targeting just the amplitude, the absolute amplitude, without really just explicit in consideration for the variability. And so with this idea in mind, so with this motivation, we just propose this methodology for selecting ground motions for component-specific target spectral amplitude and variability. So in this methodology, we start from the definition of a set-specific target spectrum for the location of interest and also the hazard level of interest. And this will be expressed in terms of RODI 50, so the median of the just 2 horizontal components. Then this is followed by the computation of what we call here the component variability ratio based on the just full population of simulated ground motions that is available. And we started here from the definition proposed by Zenji and Abrahamson in 2021, and we tailored this for the utilization of the full population of records. So we have here, just as you can see at the numerator, we have the spectral acceleration of the component of interest, so that J will be either the full normal or the full parallel. And here at the denominator, we have the RODI 50. So giving really just a clear clear and explicit measure of what is the degree of polarization of the motion. Then once we extend this calculation here across all the population of just simulations we have, for example, now on the database, 50 of them. So then we determine we calculate the median and standard deviation of the component-specific target spectrum based on the full set of simulations. And here at this point, we really just tailored this just methodology to two potential applications. So one would be on the deterministic spectrum, so as defined in the AC7, so the 84th percentile of the just ground motion models, and the other one on the conditional mean spectrum. So briefly, well, we can, as expected, you can clearly see how we see this. We can see the CVR factor, just of course popping up in the expression of the just target amplitude. And here, the effect of this CVR just factor is to really just split now the target spectrum, again, for the rho D50 for the two components. And then here we also just introduce another factor, sigma, and specifically we introduce this for deterministic. We just modify this for the conditional mean spectrum, utilizing the information on the expected aleatory variability at the site of interest coming from the simulated motions straight from the simulations into what would be the target variability for the two components. Quite interesting here, you will see that for the deterministic spectrum, we use the spread of the simulated motions for determining the target variability. But then you can see, as you know, for the conditional mean spectrum, this sigma is also going to affect the expected amplitude, so the expected target amplitude for the two separate components, with implications, that we will see in a second in a demonstration. So at the end of this step 3, so in short, really what we're going to get is that we start from one single spectrum for the median ground motion, and then we obtain the two spectra with the corresponding variability. And then finally, in the last step, what we do, we randomly select m sets of simulated ground motions. We compute the resultant normalized error, and then we sort the ground motion based on this minimum error. A couple of just notes on the way we calculated error. So first, we consider, of course, simultaneously the two components just to make sure that we use the normally for parallel from the same ground motion at the site of interest. And second, we minimize simultaneously both the median and standard deviation. In this, just format, we assign the same weight to the two, but it will be up to the designer and the analyst to potentially apply and use different weights for the variability or the spectral amplitudes. All right, so now quickly, a couple of demonstrations here of just the application of this methodology. So the demonstration number 1 will be on a 10-story building, 3D just structure, reinforced concrete building. And I'm making reference to this site A here and the 25 realizations I mentioned earlier. One thing to clarify just up front is that we are using here the 25 realizations because those are and were the realizations we had at that time, but we acknowledge that these do not represent the expected aleatory variability at the site of interest, so in this case at site A. Eventually, once we have more uncorrelated realizations that we believe that represent the aleatory variability at that site, and then we also have the same simulations for the same just scenarios coming from other software to also incorporate the epistemic uncertainty, then we would think we will have a full representation of that sigma. But still, this is not going to affect the methodology and the framework itself. Now, in this first plot here, so what we are doing, we're calculating, provide an example of how we calculate the CVR for based on one specific event. And so you can clearly see that from one motion here, from one spectrum, I should say, target, we split this into 2 for each component. Then from this single calculation, we extend this to the full population of just motions, and we obtain the corresponding median and standard deviation. Well, then, very simple, we do something that we're pretty familiar with. We select the motions here to minimize the error. And so here's an example of how we do this for the corresponding bandwidth of interest for the structure we're using. In this case, once again, this 10-story building with a fundamental period in the two direction, 1.5 and 1.7 seconds. Now, here, this plot here on the far right represents the building response. And so I'm showing here a comparison between the response obtained from the full set of simulations, the 25, and then the subset of 11, if we follow the AC7 provisions, noting that, well, in this case, we were pretty lucky we were able to capture the amplitude pretty well because the motions were all pretty close to the target spectrum. But most important here for this methodology, we were fully able to capture the distribution. So whatever distribution was in the original set of records that, once again, eventually will represent the target distribution, this will be fully captured in the variability of the structural response. Keeping in mind that we may not necessarily be interested in the just a median response, but median what standard deviation, or still have a measure, a sense of how large that spread is. Now, very quickly here, the second demonstration is on the conditional mean spectrum. A couple of just points I want to highlight here have to do with the importance of sigma. As I mentioned earlier, so this sigma is going to influence here not only the spread that we set for the two components, but the amplitude itself. And you can see this, just clearly like represented in this plot for now this site B, which is the site, we're looking at for the second demonstration. Something we've noticed is that, which was not a surprise because once again, here we're looking at these 25 realizations, correlated realizations, is that the sigma, so the spread predicted by the motions, tends to be lower than the spread predicted by the ground motion models. However, even for this limited initial, limited set of motions, you can clearly see that there are sites, this site C here, where we have just bilateral, whenever the apocenter is here, you expect to see a bilateral rupture. So for periods longer than 6 seconds, we just do see, for the full normal component, a spread that is larger than the spread predicted by the ground motion models. But of course, once again, implication of what will be now the target amplitude, target spectrum for that component. All right, so we'll jump now to the some thoughts and remarks we would like to share with you. So first, based on our experience with these motions, the physics-based simulations can just inform the selection of scenarios in terms of rupture details and also point of initiation of the rupture that lead to low probability but yet realistic strong motions, which may be used, for example, for the design of a critical infrastructure. We heard this just today a lot, where we may not necessarily be interested in the median response, but we may want to look at that one single extreme, and again, low probability yet realistic, just earthquake. Second, suites of validated site-specific simulated motions can provide invaluable data for just engineers to update and think about the next generation of ground motion selection methods and in general assessment and design just methods. Finally, if we think about future efforts for the simulations, it will be good to inform just future simulations by hazard studies in the region of interest and to make sure that we simulate the earthquakes that are most relevant to that site just of interest. So if it's a magnitude 7.2, 7.1, just a Hayward fault, that will be helpful to avoid scaling and spectral matching. And finally, just very important introduction of uncorrelated rupture realizations to make sure that that sigma that we target becomes more closer and closer to the expected aleatory variability that we expect at that specific site, so that also our responses become more representative of what is the variability we should expect in reality. And I will stop here and be happy to take any questions.
Any questions for Floriana? Are we watching the online questions? Yeah. Okay, nothing else.
Since I have already the microphone, cannot avoid. Now, a question related to this very last comment related to the, okay, it is important to be informed by hazard studies. Okay, however, the disaggregation brings not only the magnitude, but also the epsilon. And so I suppose that you have, okay, the largest contribution is magnitude 7.2 and epsilon 1. How do you think of managing this epsilon 1 within, so one should use among the various realizations the one that corresponds
right.
to the sigma equal to 1.
No, that's a very good question. So, I agree. When the result we obtained from the seismic hazard aggregation includes the magnitude distance of the site as well as the sigma. Sigma that comes from the ground motion models. And so it really becomes a question of to what extent that we want to really just keep incorporating the notion of ground motion models into our, planning even of the ground motion simulations. So it's an interesting question, well, my thought just on this is that we should acknowledge even that sigma, and to understand even within that single scenario that we target, what would be for the specific intensity measure the variability we may get. So we know that we get the aggregation for a specific intensity measure. It can be the PGA, can be the spectral acceleration, and for a specific return period. So when we select the scenarios, we may not want to look at the specific, the one single scenario in terms of magnitude and distance that come from the aggregation, but also look at a suite, a spread around, that is informed by that sigma that really can provide us more insight into what other ground motion scenarios can really fill that gap. And I would say probably just another way to look at this is to really introduce more variations in the type of scenarios we have. Again, using as a guide that spread that we get from the seismic hazard the aggregation and the epsilon.
Can you get the microphone
over? Statistics is particular, it's called a term of art, and it requires data, and it requires that the data has randomness in the data. And what you're doing, calculating a standard deviation and a mean on a model, I think falls, there used to be a Berkeley statistician here, Thomas Friedman, had a theorem of the rabbit in the hat, that unless the data has probability in it, you cannot pull probability out of the hat. You get out of the hat what you put into it. So it's not really an efficient way to look at the problem, treating models as data. Because you don't, in the earth sciences, when the problems are very broad, you have to understand the facts, the assumptions, and the limitations of the assumptions. So if you want to comment, maybe you could comment on the limitations of what you're suggesting, but you have to be very careful to not fool yourself.
Yeah, so I actually totally get your point about this being very critical, so the way we just assess the uncertainties. Also because here we are kind of just digging into one specific type of uncertainty, which is the, well, I should say variability, aleatory variability associated with the specific ground motion. So, and that's just a hard task. In addition to this, as I mentioned, we should also acknowledge that at some point we'll have the epistemic uncertainty to consider, knowing that there will be multiple platforms where the same earthquakes will be, scenarios will be simulated. And so they will also may introduce variability in the, as a function of the different rupture model and, just different structure overall simulation model. And so my answer is that the point is taken, so we should acknowledge even more how challenging this is. And, but knowing that, just understanding what are the factors that are introducing, the most important factors that are introducing and contributing to this uncertainty is just would represent a step forward. And so in other words, we do not claim that we are just capturing, as I mentioned earlier, the uncertainty here, the full uncertainty, but at least we are trying to get oriented and to understand how the simulations can help, and going from what is just an ergodic, just assumption for the earthquakes, leading to those, ground motion models variabilities, to a non-ergodic assumptions, but which will, just potentially help a lot with the definition of the uncertainties. But your point on, just acknowledging the how hard this is fully taken.